Hey everyone, I'm Nick. The purpose of this video is to describe what proof writing and learning to write proofs looks like from the perspective of a student who's really just getting to do it. So we all kind of start with a foundation of just numerical, just math, right? Applied math. We start in arithmetic, we start to add some geometry, some calculus, statistics perhaps, and eventually you just work towards more and more applied. But we kind of take a step back and we start to look at the things that we kind of thought we knew and how we can prove them. So at its simplest, proof writing is using facts, theorems, widely held mathematical beliefs to prove something that you want to assert. So you can't just have people like A.J. Bailey come tell you you're wrong. You can prove that you're right, A.J. Bailey. So let's look at an example. So a really easy example of something that you assumed you knew would be like parity or even and odd. So for the longest time, I accepted, like pretty much everyone does, an odd number plus an even number makes an odd number. Well, yeah, it makes sense to me, 3's odd, 2's even, 5's odd. It must work. And it works in every example you can come up with. And the reason for that is because it's true. However, now we get to spend a page, 2 pages, 3 pages proving that that's the case. So we're going to go through a slightly more complicated proof, and I'm going to be able to explain to you guys the proof writing process, where we get 6 steps that really help us find our way, especially where it's a little bit more complicated than 1 plus 1 equals 2, or 2 plus 3 equals 5 in some cases. So for this proof, we will prove that the limit of the inf of a sub n is less than or equal to the limit of the sup of a sub n. So I have some notes. I hope that is okay. So the first step, the very first step in the proof writing process is going to be to write your statement in an if-then format. So I do that. Step 1, my if-then statement is going to be if a sub n is a bounded set, then limit inf a sub n is less than or equal to the limit of the sup of a sub n. So, to give a little bit of an idea of what we're talking about, I have 2 very high-speed graphic examples. So, for the top example, we'll let v sub n from n equals 1 to infinity be defined as 1 over n. So we just graphically lay this out, where at n equals 1, we get b of n equals 1. At 2, we get 1/2. At 3, 1/3. And so on. So in this case, if I were to pick the inf from 1, which is the beginning of the set, it would be 0. Because we can see that this trends to 0. 0 is going to be the best bottom limit of that. Similarly, at the top, we've got the sup, which we can see is 1. Again, we see that it trends down. And then we'll go through this second example real briefly. Let c sub n from n equals 1 to infinity equal 1 minus 1 over n. So a similar set, it just starts at 0 and goes up to 1. So similarly, we can look at the inf, and at n equals 1, the inf is 1, and it's 1 for the entire set. For the sup, starting at n equals 1, we see that this trends up towards 1. So I don't think that it's going to get any higher than 1. And I can prove that, but we're actually focused on something a little bit different. Shoot. So we have our if-then statement, and what this is essentially saying is that every time, if you start, whether it's at 1 or 2 or 3 or 4 or 5, from that k that you choose all the way on to all n, the inf is going to be smaller than the sup for the rest of that set. So I I hope that makes sense. It's hard to get feedback from a video and ask people if it makes sense. So, step 2. I'm going to write down the words between if and then. So in this case, that is to say, I'm going to write down the thing that I know. So I'll call it my know. So I know that A sub n is a bounded set. Cool. Step 3. I'm going to write down everything after the word then. So this is going to be the things that I want to show. Given this, I want to show that the limit inf of A sub n is less than or equal to the limit of the sup of A sub n. Wonderful. So step 4, we're going to backtrack just a little bit. And we're going to expand the things that we know. Forgot that. Fantastic. So, a couple things that I know. I know that we're going to let this be y sub n. Pardon me, this be y sub n. So we're going to say y sub n equals the sup of AK, where K is greater than or equal to n. So again, that is to say that if I go to my examples, from 1 on, the sup is 1, that is in B sub n. From 2 on, though, the sup is 1/2. So the sup and the inf can both change, don't have to, but can both change as you get further and further along a set. So that's essentially what this is saying, is that we're going to let y of n be some series n, that if I pick 1, the sup is 1. If I pick 2, the sup is 1/2. So we put an n and we get the y for everything past that value. The other thing that I know is quite similar. Z of n is going to be the inf of A sub k, where k is greater than or equal to n. Again, if we go back to these examples, in C sub n, if I let my n equal 1, the n for the set is 0. If I let my n equal 2, the inf for everything equal or greater than 2 is 1/2. If it's 3, it's 2/3, and so on. So that is effectively what this is saying, is that it's a series that for every n greater than or equal to 1, z is the inf of the set, greater than or equal to that n. So I also know, by definition of the upper bound and the lower bound, z sub n is less than or equal to y sub n for every n greater than or equal to 1. So again, examples help. These are not the only types of sets that you can have, not the only types of bounded sets that you can have either, but visually we can look and get a kind of decent idea. Where we have, say, let's use C sub n. We have our inf at 1, and it's right here, it's at 0. So we'll call that the inf where n equals 1. We've also got our sup, which at any value we see as 1, because it trends towards 1. It's never going to decrease. So we can say that our sup, where n equals also 1, and we know it won't change, but we're going to stick with 1, at least for the time being. So what this says is that whatever value I go out to, the inf is always going to be lower than the sup, which I mean kind of makes sense. Like if we skip over, say, to 3, let's let n equal 3, then that becomes my inf. But I mean, it still works. It's still lower than the soup. So I'm pretty convinced so far. I'm definitely not unconvinced. So we're going to keep going. I also say that because I did write a proof. So I have reason to be convinced. So now I'm going to go to step 5, where, you guessed it, we're going to do the show, but we're going to expand it out a little bit. So, show, part 2. Here, I've written out that I want to show that the limit of the inf of a sub n is less than or equal to the limit of the sup of a sub n. So I can also write that slightly more mathematically as the limit as n goes to infinity of z sub n is less than or equal to the limit as n goes to infinity for y sub n. So these are the things that I had. A good practice would be to go and to box off all of the theorems and definitions and the things that you think you know, rather. So I'm going to do that. I'm going to go in, I'm going to say, these are things that I know, right? I just had a definition of y sub n and z sub n, and then I also know this. That is a thing that I know. I know that A is a bounded set. And this is what I want to show, given these things. So, step 6 would, in most cases, be for us to run a couple of examples. Luckily, we've already done that because we're skeptical. So, done. Neat. Okay, now on my very, very clean A2 Dayroom chalkboard, I am going to write out everything that we did as a clean proof. So we have the things that we need, or at least things that we think could be helpful for us to use. And now we're going to put them all together and we're going to write a clean proof, which is just nothing but, hey, this is what I want to prove, and then I'm showing you step by step how I do it. So it's a little less choppy, a little less step 1, step 2, step 3, step 4, step 5, step 6. Rather, these are the things that you need to know, and I'm going to walk you through it, and I hope to prove to you, in this case, that the limit of inf of a sub n is less than or equal to the limit of the sup. So, here goes. Okay, so this is me introducing my clean proof to the world. It's by no means finished yet, but here's where we are. I say that I will prove that the limit of inf a sub n is less than or equal to the limit of the sup of a sub n. So I introduce a couple of definitions. So I say that by definition of upper bound and lower bound, c of n is less than or equal to y sub n for each n greater than or equal to 1. So I say that this means that y sub n minus c sub n has got to be greater than or equal to 0 for all n. So, since both limits exist in a bounded set, I will let L equal the limit of y sub n minus z sub n. And again, since I claim that this is true for all n, I say that the limit L is greater than 0. So, I now introduce the way that I'm going to prove this. I want the reader to be tracking along. I don't want to give AJ Bailey any reasons to poke holes in my proof. So I'm going to say, hey, AJ, assume to the contrary that L is greater than 0. Pardon me, L is less than 0. Recall, I just said a couple moments ago that L is greater than 0, or at least I claim that L is greater than 0, since it's the difference between the sup and the inf, or the limits of the sup and the limit of the inf. Then, if that's true, then by definition, there's got to be some epsilon greater than 0, such that L plus epsilon is less than 0. right? If L is less than 0, some little tiny positive number is going to keep it under 0. So now, I'm going to say that since these are supposed to converge, then there has to exist some n, right, where for all little n greater than big N, yn minus z sub n minus L is either less than or greater than epsilon, depending on it's an absolute value. So the absolute value of y sub n minus z sub n minus L is less than epsilon. So this means that L minus epsilon is less than y sub n minus z sub n, which is less than L plus epsilon, which is less than 0. And just to remind ourselves, recall that L is defined as the limit of y sub n minus z sub n. All right, so given this inequality, this creates a conundrum. I'm pretty sure I spelled that wrong. But it creates a problem where y sub n minus z sub n has got to be less than 0. But remember, we defined earlier that y sub n minus z sub n has to be greater than 0 for all n by definition of the sup and the nth. So essentially, what we just did was we took this concept where we supposed that at some point this line could be greater than this line. But this has to be at the bottom of the set, and this has to be at the top of the set, so that doesn't really work out. So conceptually we got it, but now we've gone and we've shown mathematically that if we assume the opposite, we run into problems. So next, we're going to talk a little bit about the proof guide, even though I am 10 minutes over time, and I will cut lots of this out. So we have 5 bullets, which say, my proof defines all variables used. My proof uses words to explain all algebraic transformations. My proof clearly states where I'm using the hypothesis, or the no, as we wrote a couple of times. My proof states what method or approach I'm trying to use. Contradiction in this case. Others include cases, contrapositive, direct, things of that nature. And then I cite all definitions and theorems correctly and rely on their mathematical formulation. So the purpose of the proof writing checklist is to make sure, again, that you haven't left any big holes for someone to come and poke at your proof and tell you that you're wrong, even though you know you're right. So thank you for watching, even though you're either Dr. Thomas or Dr. Thomas made you watch it in class.